Welcome to this module of Professor Messer's free CompTIA Network Plus certification training course, the online training course that's like the first morning dew on a brand new day. I'm James Messer, and in this module we're going to talk about IPv4 and IPv6 routing protocols, and really comes from our Network Plus exam in 10-004 section 1.5, where we need to identify common IPv4 and IPv6 routing protocols, and there's three different categories we need to know about. We need to know about link state, we need to know about distance vector, and we need to know about hybrid routing protocols. And there are some examples of routing protocols in each one of those. And we're going to step through them, what the similarities are, what the differences are, what you need to know about those routing protocols. So let's start with link state routing protocols. The link state routing protocols get their name because the information that routers talk amongst each other is related to the link, how the link is, the current connectivity. If the link is up, then you can go there. If the link is down, you can't go there. Pretty basic, pretty simple in the way that it operates. But there are some very complex protocols that determine if a link is available and if we can route between those. This is very scalable in the way that it operates. It's used very often in very large networks because understanding the state of the link is oftentimes a complex process that involves a router understanding a lot about the entire network. We'll also talk about these two types of link state routing protocols. There's two that we need to know for the Network Plus exam. One is called OSPF and the other is called ISIS. So let's step through the first one, OSPF. OSPF stands for Open Shortest Path First. That sounds very much like a link state protocol, doesn't it? And it works just like it sounds. If a link is open and it's the shortest way to get there, that's where we should go. Sounds pretty simple. The idea behind it, though, is that we're grouping our networks into areas. This is used very often on very large networks. And so there are areas, pockets of networks that we create. And what we'll do is route between each one of those types of pockets. Now, the default area in OSPF is area 0. You'll see this very often. In some OSPF networks, there's only one area. It is one big area 0. On larger OSPF networks, there might be an area 0, area 1, an area 2, area 3, or many others. Now, each area is in charge of keeping track of its own database of link states. And so you'll see that each one of those is really a world into itself. There's an area just keeps track of everything in its area, and then between the different areas, the routers keep track of what's going on between those. And so it's really segmenting out the processes that take place for routing. You'll see this a lot with routing protocols. Each link has something called a cost associated with it. So one router might have 10 different links connected to it. So it needs to determine how to move traffic down those connections. It's going to look at how much it costs, if you will, to go down those links. And it takes into account what the throughput, how fast and how much traffic's going through there, how reliable that link happens to be, how often does it go up or down, how does the traffic go through, round trip time, how quickly does traffic go back and forth over that network. The lowest cost wins. So the smallest cost we're looking for is what's going to go through that link. If we happen to have two links to the same network and they have the same cost associated with them, OSPF does something called load balances. It uses both of the links and sends traffic down and separates the traffic out so that you can take advantage of having multiple links to a location. If you happen to lose a link, it just uses the other one. It knows that we lost link state there and it uses that. So there's also some redundancy capabilities built into that as well. OSPF is really good at determining when something changes. We're going to talk more about this idea called convergence in the next video. But these changes in network link state are really important in a routing protocol because you want your network to be able to recover quickly. And OSPF is one that does recover very quickly, usually within seconds. It's able to determine that a link is down and start routing traffic through a completely different connection. OSPF, though, is a very complex protocol. You don't really see it in smaller networks. It's really for very specific purposes because there is a lot of complexity that deals with it. But if you're familiar with OSPF, you're using OSPF in your environment, then you know a lot about using this particular kind of routing protocol, and most likely you're on a very large enterprise type network. Another link state protocol that's important to know for your Network Plus certification is one called Intermediate System to Intermediate System, or ISIS. This is not as popular as OSPF, but it is implemented in some very, very large-scale networks. You usually see this in service provider networks. It's not often in the smaller to mid-size enterprise type networks, but in large government networks, large service provider networks, you certainly see an ISIS routing protocol used in those environments. This also uses a concept called areas to be able to communicate. It worked for OSPF. It certainly works very well for ISIS. One thing that's a little different about ISIS is that it uses different levels of routing. This is also very similar to OSPF in the way that it works, in that there's a level 1 that routes within an individual area, and then there's also a level 2 that routes between areas. It's very well laid out, very structured in the way that it works. Theoretically, you can scale an ISIS routed network to be much larger than OSPF, which is why you really see it in those massively large environments, primarily because it doesn't send quite as much information back and forth between routers. We call it less chatty in the way that it operates, and that's probably why service providers really like it, because with service providers, government networks, really large-scale networks, you never know exactly the type of network link you're going to be going over. It may be a very slow link, it may be a very fast link, it may be a non-terrestrial link, it may be using satellites to communicate, so it needs to be as efficient as possible and yet still be able to support a large-scale network and be able to route traffic through each one of the pieces on that network. Another type of routing protocol is something called a distance vector routing protocol. Now, with our link state routing protocols, we took a lot of different variables into account. We looked at how far away a link was, the type of throughput we were getting, what the total amount of traffic going through it, and response times we were going through a link, and we calculated a cost, and we chose the one with the less cost. Distance vector, much simpler in the way that it operates. It only wants to know how many hops away is another network. And that's another way of saying how many routers do I have to go through before I finally get to that other network. And then it decides what the vector is it should use based on distance. Now, it doesn't know how fast the networks are between here and there. It knows that if I need to get to that network, I can go on this link that has 4 hops to get there, or I can go on this link that has 6 hops to get there. It's going to choose 4. Now, the one with 4 hops might be through very slow networks, but that's not what distance vector does. It only knows hops. It only knows distance. That's all it worries about. Now, what's nice about distance vectors, configuring this is very easy. Essentially, you turn it on and it's done. There's not much you have to configure in these types of routing protocols. They're usually very automatic, and therefore they're used usually in these small to mid-size environments, and even larger organizations would use distance vector routing protocols because that's all they need. Maybe they know all of their links are relatively fast. You don't have to do any fancy load balancing. We'll just use distance vector, and we're just fine with using those routing protocols to do what we need. One type of distance vector routing protocol is called RIP, RIP. And there's also another version of RIP called RIP version 2. This stands for Routing Information Protocol. This is one of the more common routing protocols you'll find. The version 2 version of this was updated for our classless interdomain routing, our CIDR block notation routing. It also includes some authentication to verify the routers are really getting a response from a real router that they happen to know about. And there's some other enhancements in version 2 as well. But the RIP is something that you see supported in almost all routing technologies. It needs to know what network address it's going to, the number of hops, and what direction it should be going to get there. And that's it. Pretty simple in the way that it operates. The maximum number of hops that RIP and RIP version 2 can support is 15. If a link is more than 15 hops away, you really can't use RIP to get there, because RIP will not automatically keep track of anything beyond that. It is, as I mentioned, a very popular routing protocol, even in extremely large networks where you don't have to worry about large number of hops. It works very well, and it's automatic in the way that it works. Another kind of protocol that we used in a distance vector environment is something called BGP. BGP is the standard routing protocol for all of the internet. When you connect to an internet service provider, you're probably going to connect and use it via BGP if you're not doing something like a static route out to that connection. And it's used by, of course, all the internet service providers. And because everybody on the internet is using BGP, they're all able to communicate between each other. If somebody else out there tried to use some other type of routing protocol, they could drop right off the internet. So it's important that everybody came up with this one style of communicating the routes out on the internet, and this was one way to do it. It's extremely flexible. You can not only use it to communicate outside of your environment, but you could also use it as what we call an internal border gateway protocol, where I'm talking within networks that are inside of my network. So however you set up BGP, it can talk outside of your network. You can use it inside of your network. It's very flexible in how it operates. And one way that many companies use BGP, many organizations will use BGP, is they will have multiple service providers for their internet link. They'll buy one connection to the internet from one company, they'll buy another connection to the internet from another company, and they'll connect them both at the same time and use them simultaneously. That's something called multi-homing, and it allows you to use these multiple links into the internet so that you're able to take advantage. If you happen to lose a link from one provider, at least you've got the other link available so that you can maintain that internet connectivity all the time. Now, if something doesn't fall into the distance vector and it's not a link state protocol, it may be using aspects of both of those, and we call those hybrid routing protocols. The hybrid routing protocols do a little bit of one and a little bit of the other, and there's really one what we call a hybrid type of routing protocol called EIGRP, which stands for Enhanced Interior Gateway Routing Protocol. It is a proprietary link state and distance vector protocol from Cisco. It's one that is proprietary to their routers, but it's very easy to set up and run. It's almost taking the ease of use of a distance vector configuration and combining it with the flexibility of the link state protocols all in one. And that what it looks at is things like total delay, minimum bandwidth, reliability, and load. It tracks all of those types of statistics, and it determines what the best link is based on those things. Very little configuration you have to do for that, and it's all handled automatically. Let's review some of the things we've learned in this module. From our routing protocols, what is an example of a link state routing protocol? Just pick any one of them. And if you recall back, there were two that we looked at in this module. We looked at OSPF and we looked at ISIS. Either one of those will work as an answer to this question. Another question, what kind of routing protocol is RIP? We've also got RIP v2, and both of those are distance vector routing protocols. The last question we have is that Cisco has a proprietary routing protocol that they use in their routing devices, one of the options to use in their routing devices. What is their proprietary routing protocol called? And it's called EIGRP, the Enhanced Interior Gateway Routing Protocol. Hopefully that's given you an idea of some of the things you need to know for your routing protocol part of the Network Plus certification. We've looked at link state, we've looked at distance vector, and we've looked at hybrid, and now we've got a pretty good idea of the types of routing protocols used all over the world. If you'd like to look at more Network Plus videos, participate in our message boards, and much more, you can visit our website, freenetworkplus.com.